We'll talk about counting disjointly occurring events.
Okay, thank you, Dr. Z. I tried to clean the filter, but I failed. So I'm still being told to clean the filter, which we'll see how long that stays on there. Okay, so the setting here is we're talking about the Boolean cube, so 0, 1 to the n, to the d, I think I said. So as a product probability space, the probability that the ith coordinate is 1 is p sub I, and it's 0 otherwise, and the p sub i's can be different, although frequently in applications they're the same. Okay, so this is a wildly general framework, even though it's not always kind of viewed explicitly that way. So, for example, the random graph GNP is an example of this. So we have n choose d is n choose 2, so we have n choose 2 basically coordinates or bits that we're choosing, and all the pi's are the p of the GMP, and so you go through the coordinates, which are the edges, and you flip the coins, and you generate some graph. So that's what I drew here, right? So there's a little baby GMP, and those were the outcomes of the coin flips, which corresponded to the edges. Okay, so an event in this space is just, there's no measurability concerns, it's just a subset of the space. So example of events in GNP, okay, contains a triangle, it looks like we contain a triangle, containing a Hamiltonian cycle, so containing a P3 as an induced subgraph. Okay, so anyway, events. Okay, so what is a certificate for an event? Okay, so you want to convince me that an event, or thinking about a certain event in this space, you want to convince me it happened, but you're lazy, and so you don't want to show me the entire outcome, show me all the coin flips. So you want to show me only the outcomes of a small number of the coin flips. So a certificate is basically a way to prove that the event occurred by showing me only a small number of the coin flip outcomes. So that's what those first two lines, that's what the top half of the slide says. So, right, to be precise, it's a subset of the set of coordinates, and also an assignment of zeros and ones on that subset of the coordinates, such that no matter what happens, as long as you agree with that assignment on that set of coordinates, you're guaranteed to be in the event. Right?
With high probability?
No,
also.
for sure, guaranteed. Okay, and right, so as I was sort of alluding to before, the idea here is that we try to think, so as far as certificates go, the smaller the better. So, well, first let's see an example of a certificate. So we were before looking at the event, so GNP contains a triangle. Right, so if you want to be sure that GNP contains a triangle, you don't have to look at every single coordinate. All you have to do to convince me that GNP contains a triangle is show me a triangle. Right, so in particular, right, these coordinates A, B, A, C, and B, C, you show me that I got ones there, then no matter what happens elsewhere, I know I'm in the event. Right. So,
but you could be in the event without, it could be a different triangle.
Absolutely. Right. So I'm not guaranteeing that if you're in the event, then you get these. But the converse is a guarantee. So it's a good point. So there are lots of different certificates for any particular event. In particular, if this is a certificate, then we can add more coordinates to it and specify them however we want, and we still have a certificate. So suppose I put zeros here. That would still be a certificate, because if I promise you that I have 1, 1, 0, 0, 1, and whatever else over here, then in particular I promise you that I have 1, 1, and 1 here. So the zeros were sort of extraneous. I didn't need to give you that promise. Right? So the point is there are lots of certificates for a particular event, And so what this black part here is trying to capture is the idea is we'd like to think the smaller the certificate, the better. Right? In particular, there's no reason to ever care about a certificate that's not at least minimal in terms of the number of coordinates that it promises. So, of course, not every event has a small certificate. For example, every event has a certificate, every non-empty event. But not every event has a small certificate. For example, an event that's a singleton, in order to prove to me that you're in an event that's just one point, yeah, I have to examine every single coordinate. But there are also non-stupid examples. For example, so what about the event that you have exactly an even number of ones that you got when you flipped your coins? There's no small set of coordinates that you can show me the outcome on in order to prove that globally I have an even number of ones. Anyway, so we tend, spiritually, we tend to be interested in events that have small certificates. Okay, so just more examples for the events that we were talking about before. So this, up there, if you promise me that I don't get edge AE, and I don't get edge BE, and I don't get edge CE, then that's a certificate that GNP is not Hamiltonian, because, well, right, this is probably clear, but because what you need at the very least in order to be Hamiltonian, you need every vertex to have degree at least 2. So if I show you a vertex of degree at most 1, then I'm not Hamiltonian. Down here, okay, so this certificate has both 1s and 0s in it. So if I show you these coordinates, which correspond to, right, so these 3 edges and these 3 non-edges, then I have proven to you that I have an induced P3. Okay, so disjoint occurrence. So 2 events, or many events, occur disjointly if A, they all occur, and moreover, they occur with certificates that are disjoint. Okay, so I guess let me just emphasize this turquoise obvious remark here. So in particular, in order for a set of events to occur disjointly, they all have to occur. Right? So the event that these n events, E1 through En, occur disjointly is a subset of the intersection. So here's an example. So remember from a few slides ago, so A was the event that GNP contains a triangle. And B was the event that it's Hamiltonian, so not B is the event that it's not Hamiltonian. So in this particular case, they occur disjointly because, well, the green 1s are a certificate for containing a triangle, and the red 0s are a certificate for not being Hamiltonian, and they don't use any of the same coordinates. Okay, so C was the event containing an induced P3, so, and that happened, right? There's an induced P3 in that graph. But it's not the case that a box C occurred, because you can't find disjoint certificates of both the existence of a triangle and the existence of a induced P3, right? Because any induced P3 uses one of these 2 edges, and those edges are both in the triangle.
P3 is 3 edges or 3
Oh, yes,
vertices?
yes, edges, right. Of course, otherwise you could. Okay, so the history here. So 1985, Berg-Kesten, a seminal paper, introduced the idea of disjoint occurrence of events and proved what's now called the Dk inequality, which is that, well, it's that. For any, if you have two events, A and B, and they're increasing in the space, which means that changing some zeros to ones never exits the event, then the probability that they occur disjointly is at most the product of the probabilities. So how do you sort of think of this? Well, okay, so here's an observation. So if A is a increasing event, then no non-stupid certificate for A ever promises a 0. Right? If A is increasing, then every certificate should only promise 1s, because if you promise a 0, you don't have to make that promise, because it's an increasing event, so if you flip that 0 to a 1, you'd still be in the event. And so you can, am I making sense? So you can forget about that promise, because whatever happened on the other things, it doesn't matter whether that coordinate was a 0 or a 1. Right? So, so A box B, you want disjoint certificates for A and B. They're both increasing, so what's the intuition? I mean, it's like they're kind of fighting for the ones that showed up. Right? You flip your coins for the coordinates, and you want to say that A and B occur disjointly. Well, for that to happen, right, we're only interested in the ones. Some of the ones I'm going to use to find a promise for A, some of the ones I'm going to use to find a promise for B. Well, so what it's saying is sort of the best that can happen is if A and B kind of don't talk to each other at all. If A and B are independent, sort of strongly independent, okay, so let's look at a particular example. So, suppose A is the event that the first coordinate comes up 1, and B is the event that the second coordinate comes up 1. Right, so those are two independent events. And well, so the only certificate for A, the only certificate for the event that the first coordinate comes up 1, the only non-stupid certificate is showing that the first coordinate is a 1. And similarly for B, the only non-stupid certificate that the second coordinate is a 1 is showing that the second coordinate is a 1. And in that case, when the events are independent like that, the inequality is satisfied with equality. Right, so I guess the spirit sort of is that if you want to make the event of disjoint occurrence as likely as possible, the best you can do is to make the events independent. So it took me some time to kind of wrap my mind around that. But anyway.
So have mercy with us.
What?
Have mercy with us.
So, questions? Is this?
How hard of a paper is that to prove all of it? I mean, in the original case, in the 85 paper?
So that's an interesting question. I mean, the paper itself is sort of a little odd historically in retrospect because they kind of buried the lead. I mean, this inequality, I think, it's probably fair to say by far the most important element of that paper, but it's kind of like 3/4 of it's like way buried back in the end of the paper, and it's not really emphasized.
Is this Berg-Kesten?
I think so, yeah. But if you kind of back out the proof from the various lemmas in different parts of the paper, it's not hard.
Okay.
And so, okay, so in the same paper, so the Dk inequality is that. The Dk conjecture is that that same inequality holds without the requirement that the events be increasing. And I have no idea why they thought that might be true, except that it is true. So, I mean, there's that. But anyway, so as far as I understand, this was a very popular thing to work on for a decade. And supposedly a lot of, I mean, I wasn't around, but a lot of people worked on it. And there were partial results. But anyway, it was finally solved in '94 by David Reimer, who was, my understanding is he was a grad student here at the time. And so the Dk conjecture became Reimer's theorem, which is, okay, for any events A and B in the Boolean cube, probability that they occur disjointly is the most of the product of the probabilities.
Was that his thesis with Kahn?
I don't think he was a student of Kahn's,
No, I
I think
actually.
he was.
No, Beck. Officially it's Beck.
I thought it was Beck also, but it
Okay.
should have been part of his thesis. I don't know if it was. Although we could go down to the library and check. Anyway, so for whatever reason, this wasn't published until 2000. At least it wasn't published by Reimer until 2000. It appeared in print well before 2000 in expositions by other people who had heard lectures about the result. But anyway, it wasn't published by Reimer until 6 years later. Yeah, so there's something called the Butterfly Lemma that goes into proving Reimer's theorem. This is much, much harder than Dk. So I think a large percentage of the graduate students in the audience were in Jeff Kahn's extremal combinatorics course, whenever that was, and he proved this, but it took 2 or 3 lectures, I think. And there's a butterfly. Okay. Okay, so our results. So the story there, I mean, as far as either of us, Jeff Kahn or I, am aware, it's new, or at least it appears not to be in the literature anywhere. It's a little bit difficult to believe that it's actually new because, well, you'll kind of see, it's sort of an obvious thing to think about, and then, as I'll show you, the proof is pretty similar to the proof of the original Dk inequality. Not even the Reimer one, which is harder, but the Dk. But in any case, yeah, it is apparently not in the literature anywhere, which doesn't mean it's not known, but anyway, here it is. So now we have as many different events as you want, so not just 2. They all have to be increasing. Okay, so x is a random variable that's defined on the space we're thinking about, on the cube, that counts the maximum size of a set of these things that occur disjointly. Right, so maybe we have 20 events, and we go through our coordinates and flip the coins for our coordinates. We get an outcome, and x goes through and says, okay, maybe, okay, these 4 of them occur disjointly, these 6 of them occur disjointly, these other 12 of them occur disjointly. So x looks at all the different possible subsets of the events and returns the largest number of them that occurred disjointly. Okay, so that's a random variable. Y is another random variable, which is just the distribution on how many of them would occur if they were all occurring independently. Right, so this is the sum over all the events of the Bernoulli of the probability of the event. Right, so these are just Bernoulli, 0-1 coin flips where the probability of each one is the probability of each of these events overall, and then we're just summing those up. So this is just saying, if the events were completely independent of each other, all of them, this would be the distribution of how many would occur when we flip the coins. Okay, then, right, so this is the setup. Then, so for all k, the probability that x is at least k is at most the probability that y is at least k. What does that mean? Well, so there's a word for it. It's x is X stochastically dominates Y. It's just a name for this condition. What it means is that if you're a betting man and you want to place a bet on one of these being bigger than the other, you always bet that Y is going to be bigger than X.
So wouldn't it be Y dominates X?
Yes, it would. Yeah. Okay. So maybe something subconsciously was why I paused there. Yeah. So X is stochastically dominated by Y, or yes, right. So I'll fix that. So the spirit is kind of the same as it was for BK. So in BK, so I mumbled a bit, and I sort of eventually convinced myself, and maybe some of you, that what BK was kind of getting at was that if you want, is that disjoint occurrence is kind of harder than in the independent case. In order for the two events in BK, in order for the two events to occur disjointly, that's harder than it would be, or at least as hard as it would be if they were independent. So it's a similar spirit here. This is what's actually going on with when the events have all their whatever weird dependencies. And this is what would be going on if they were all independent. And what this is saying is that if they're independent, you're likely to get more of the events happening than if you are forced to find disjoint occurrence of the dependent ones. Okay, so now it's really unfortunate that the please clean filter is still up here because I have an important remark at the bottom here, which is that the Dk inequality is exactly the n equals 2, k equals 2 case of this.
And the Riemann generalization makes sense in this context?
Excellent question. I'm literally about to get to that. So just to remind you, so this is not the Reimer general. This has nothing to do with generalizing Reimer because it's crucial here that all the events be increasing. But I'll get to your question. Right. So suppose that n is the number of events, k is this k here. So suppose we took n equals 2 and k equals 2. So n equals 2 means we have two events. And k equals 2 means, what does this translate to? The probability that x is at least 2 is the probability that e1 and e2 occur disjointly. Right? X is the thing counting how many occur disjointly. So if x is at least 2 and there are only two events, that means that they occur disjointly. So if n equals 2, k equals 2, on the left-hand side, we have what's on the left-hand side of bk. And on the right-hand side, well, same thing. So if there are only two events, y is at most 2. It's a sum of two Bernoullis. It's at most 2. So if it's at least 2, then it's 2. And what's the probability that it's 2? Well, the probability that both of these Bernoullis come up 1, which is the product of those probabilities. Okay, so, well, yeah, so that's that. So, right, so before I answer Dr. Z's question, let's just see a quick example of some place that this might come up. So, triangles in GNP. I think triangles in GNP are sort of a prototypical example, like, of everything in this kind of field. So suppose we were to try to apply the result that we just had to say something about triangles in GNP. So let's make each triangle an event. So each potential triangle is an event. So there are n choose 3 of them. And they're increasing because, so of course, I guess I didn't say this explicitly, but when I translate a triangle into event, what that means is the event is GNP contains that triangle. Right? And of course, that's an increasing event because if I add more edges, I never lose that particular triangle. So I have n choose 3 increasing events that correspond to the potential triangles. So x all that's doing is it counts the maximum size of a pairwise edge disjoint set of triangles. Right, so that's a totally reasonable question that might come up in combinatorics. What's the maximum number of pairwise edge disjoint triangles you can find in GNP? Okay, Y is a binomial with parameters n choose 3 and p cubed. Right? We have n choose 3. So before, Y was a sum of Bernoullis. Now all the Bernoullis have the same probability, which makes it a binomial. So there are n choose 3 events. Each one is occurring with probability p cubed. So this is what the distribution on the number of triangles would be if the triangles were all independent, which they almost are, but they're not. Okay, so then what does the result say? So, so the probability that x is at least k is just the probability. So x being at least k is exactly the statement that there are at least k pairwise edge disjoint triangles. Okay, so then the probability that there are at least k pairwise edge disjoint triangles is at most the probability that this binomial is greater than k, is at least k. And that's beautiful because obviously the right-hand probability is very well understood. The probability that binomial is big, we know what that is, that's Chernoff. So if we want, so if k is, say, a small constant factor bigger than the mean of the number of triangles, then Chernoff gives, so then this k would be, let's say, 1 plus epsilon times n choose 3 p cubed. Right, so the mean is n choose 3 p cubed, and if we're letting k be sort of an epsilon constant bigger than that, then Chernoff gives a very tight bound for this. And so we get a tight bound for this, which is great. Okay, so Dr. Z's question. So, right, so our result generalizes Dk. Is it reasonable to hope for the corresponding generalization of Reimer? In other words, is it possible to remove the word increasing from the result? So any guesses? No. It has to be. Okay. Cat's out of the bag. Of course not. So Soviet Russia was no. So there's an easy counterexample. There's a counterexample in dimension 1. So just flip a single coin, a single fair coin. E1 is the event heads, and E2 is the event tails. X counts the maximum number that occur disjointly. X is automatically 1 because the coin is either heads or tails. But Y, there's a 25% chance that Y is 0. Yeah, right? It might happen that, yeah, of course. So so this fails for k equals 1. Right? The probability that x is at least 1 is the probability that it is 1, which is 1. And the probability that y is at least 1 is only 3/4. But it should be greater than 1. At least 1. Okay, so you can't hope for that. Okay, so picture. Right, so for the result,
It's possible to have some conditions to resurrect it that will avoid this obvious example and make up more conditions.
Yes, maybe. It's not something I thought about at all. But I mean, there's a. I think that. I mean, so we try to think about what's kind of going on that kills that example. So the problem is that they're disagreeing on what happens on a coordinate, and so that kind of artificially increases x in the sense that, you know, x can count on something happening in that coordinate however it comes up. I don't know, I'm mumbling obviously, but